Dear colleagues, I guess we can start. So it's my pleasure to introduce you our today's speaker, Mr. Evgenii Mitsai, who is likely to become doctor shortly. So he will tell us about his work on chemical inert sensors with temperature feedback based on optically resonant semiconductor nanostructures. So Evgenii is visiting us from Institute of Automation and Control Processes of Far Eastern branch of Russian Academy of Sciences. So the guest is really from far away, but he's here offline with us. There is a small hint on the format. So Evgenii is giving us a presentation, like 20-25 minutes. So please do not interrupt him. We will have chance to ask questions after the talk, just to fulfill the format of PhD defense. So Evgenii, please, the stage is yours.
Thank you. Thank you. So, good morning or good afternoon, dear colleagues. So let me present you my work. So let me start with a short introduction. So identification of organic pollutants, explosive and narcotic substances is urgent problem in the fields of ecological monitoring, medical diagnostics, and forensic analysis. And to solve these problems, non-contact optical methods of signal registration are often used. In particular, sensitive and selective method for identification of molecular analytes is Raman scattering spectroscopy, which is based on the optical process of inelastic light scattering with a change in its frequency. And new spectral lines appear in the spectrum of scattered monochromatic radiation, and the position and intensity of new lines helps to identify irradiated substance. Raman spectroscopy allows to identify molecules in ultra-low concentrations with the possibility of working with laser pumping wavelengths in near-infrared range. But the main disadvantage of this method is really low Raman scattering intensity, about 3 orders of magnitude lower than Rayleigh scattering intensity. Nevertheless, this disadvantage could be avoided if we use so-called surface-enhanced Raman scattering, which is based on the interaction of molecules with the nanoscale optically resonant nanostructure that localize incident laser radiation in the vicinity of the surface, which leads to the formation of electromagnetic hotspots. And enhancement factor of SERS is proportional to the force power of local field amplitude, and molecules located in such fields have their SERS signal enhanced significantly. And plasmonic materials are often used to create such nanostructures, in particular noble metals that maintain local plasmon resonance and provide electromagnetic enhancement factors enough to detect even single adsorbed molecules. But the using of metallic nanostructures has some disadvantages. First is heating of metal nanostructures due to high ohmic losses in metals, which with difficulty in direct measurement of heating temperature values of nanostructures during SERS measurement can lead to thermal destruction of adsorbed molecules. And second disadvantage is chemical activity of metals, which leads to the change in the initial structure of adsorbed molecules, which can lead to inaccurate identification. And so these disadvantages could be avoided by use of semiconductor nanoparticles, which also can localize incident of laser radiation due to mirror resonances. And high index materials are often used with low ohmic losses, for example, silicon or titanium dioxide, which also have their own intrinsic temperature-sensitive Raman band that helps to control the measure and control local temperature of nanostructure during measurement. A series of works have already been devoted to the study of local thermometry of semiconductor nanoparticles, mostly of spherical shape, and another series of works were devoted to the study of features of chemical interaction of adsorbed molecules with plasmonic nanoparticles during SERS measurement. But for semiconductor nanoparticles, such structures have not been carried out. So, from the point of view of sensor implementation that is capable of carrying out measurements that are non-destructive, non-invasive, and time stable, it is important to investigate the chemical interaction of adsorbed molecules with semiconductor nanostructures during SERS measurement and the effect of local heating of nanoparticles on the SERS measurement result. So the aim of the thesis is to study the physical principles of creating chemically non-invasive thermosensitive SERS platforms based on optical resonant semiconductor nanostructures. So the following objectives were set and solved: to develop high performance and flexible fabrication methods of optical resonant semiconductor nanostructures to control the topology, chemical composition, to study the interaction of the molecular analytes with semiconductor and plasmon active nanostructures by SERS spectroscopy, to study features of local laser-induced heating of molecular nanostructure system by optical spectroscopy of thermosensitive Raman bands, as well as possibility to control efficiency of nanostructure heating by tuning chemical composition of nanostructure, and to study how laser-induced local heating of semiconductor nanostructures affects SERS signal from the adsorbed molecules. So the example of SERS platform is a so-called black silicon surface, which is fabricated by chemical etching of standard silicon wafer in the oxygen fluorine containing atmosphere. And as a result of such etching, randomly arranged cone-shaped nanostructures are formed on this surface. And standard method for determining the chemical activity of SERS substrate is deposition of model analyte on it, paramethiophenols or PATP in short, which has high affinity to noble metals and has high intensity Raman bands. And measurement on a chemically active substrate leads to the dimerization of PATP monomer molecule, and it transforms to another molecule to dimer coupled benzene, which leads to the identification of several new lines in the Raman spectrum. So Raman measurements were carried out on a black silicon surface after deposition of PATP molecules in different time intervals. And as you can see, regardless of the irradiation time, only PATP lines appear in the Raman spectra. And similar measurements carried out on black silicon surface, but covered with a thin layer of silver, results in that already after 20 seconds of laser radiation, DMAB lines appear in the Raman spectra, which tells about quick conversion of PATP molecules. And by the monitoring the evolution of intensity of the DMAB band, we can estimate the rate of this chemical reaction. So these results allow us to conclude that black silicon surface is chemically inert. So what is deposited on it is detected, and in the case of metallized surface, another molecules are found. So to carry out measurements that are reliable and yeah, so we need to use chemically inert black silicon substrate. From the standpoint of sensor implementation, it is also important to rate to measure rate of chemical reactions occurring in liquids. So chemically inert substrate also provides a local field amplification and without disturbing the SERS spectra. And to induce photochemical reactions on such substrate, so black silicon surface was immersed in a sealed cell filled with PATP molecules in methanol water solution. And to induce photochemical reactions, silver nanoparticles were added to the solution, and the solution was exposed to sunlight that, with the help of nanoparticles, induces this chemical reaction of dimerization. And so Raman measurements carried out on this the system demonstrated only after 4 days of sunlight exposure DMAB bands appear in the Raman spectrum. Similar measurements on the surface without silver nanoparticles demonstrate no conversion, so only PATP bands, and measurement on metallized surface demonstrate quick conversion of PATP molecules in the near surface layer, and this substrate becomes insensitive to the actual changes in the solution. So using of black silicon surface with the addition of silver nanoparticles allows to rate the chemical reactions occurring in liquids. So first scientific statement, chemically inert nano-textured silicon without any plasmon active coating allows to non-invasively identify model molecular analytes with detection limit of 10 to the power of -6 mol and an average SERS enhancement factor of 10 to the power of 3, as well as to the two trace kinetics of the catalytic conversion of paramethyl ethanol to benzene in methanol water solution stimulated by sunlight radiation and silver colloid. So it is important to note that during Raman measurements, one often works with organic molecules that have rather low temperature of thermal decomposition. So it is really important to control the temperature of nanostructures during SERS measurement. But in the case of previously used substrate of black silicon, there are several nanospikes in the focal spot of the laser. So it is difficult to study the effect of individual structure to the Raman spectra. So to be able to study the effect of individual nanostructure, another substrate was created, which is arranged array of silicon pillars. It was fabricated by lithography method with the help of polystyrene nanospheres, and distance between pillars was chosen according to laser focal distance to the size of the laser focal spot. And thermometry features were studied with the help of intrinsic silicon Raman band, which correspond to phonon mode of its crystal lattice, and the resonant frequency of which depends on temperature. And according to spectral resolution of spectrometer that measures identifies the position of silicon peak in Raman spectra, we can estimate the accuracy of temperature measurement, which is about 20 Kelvin. And experiment was first we irradiated a single pillar with a CV laser with a gradually increasing intensity, recording Raman spectra and looking and observing change in the geometrical shape of nanopillar during the SERS measurement. And from the obtained results, we can see that threshold intensity at which top of the structure melts is 42 milliwatts by micrometer squared. And but the heating value of 400 Kelvin, determined from the position of the shift of the silicon peak, is significantly lower than silicon melting point. And also at high intensities, clear asymmetry of this curve. So we detect asymmetrical peak. So to explain these features, numerical modeling was carried out. So result of which is you can see here. So you can see top of the structure heats up more and base less due to heat transfer to the substrate. And on this picture, you can see similar calculation, but for wider range of intensities. And this curve represents heating value of top of the structure. This curve is base heating value, and the circles indicate experimental results of temperature measurement from the position of the shifted silicon band. And so a symmetrical peak could be presented by the sum of several symmetrical ones that correspond to evenly heated areas of the nanostructure. And uneven heating of pillars could be more clearly represented by mapping the Raman signal distribution. So these maps represent the areas with the same temperature, and initially at low laser intensity, no features were found, and at higher values of laser intensity, signal from unheated silicon is located at the outer boundaries of these pillars, and signal of heated silicon is located more in center zones. And transformation of shift of silicon band values to the heating values and computer post-processing allows to get this more clear temperature distribution map of triple pillar. And spatial resolution of this temperature measurement reaches 150 nanometers. So second scientific statement, Raman spectroscopy of resonant silicon pillars allows to map the local temperature distribution in non-10 analyte system with an accuracy of 20 Kelvin and lateral distribution resolution of up to 150 nanometers. So the controlling of local temperature in a system of nanostructure and analyte plays key role for carrying out measurements that are time stable. At the same time, controlling the efficiency of laser-induced heating of nanostructures, and also in the direction of increasing of this efficiency opens up prospects for various physical, chemical, and biomedical applications. For example, for realization of effective photothermal converters, hypothermia of oncological diseases, and controlled pyrolysis. So in this regard, we investigated possibility of increasing of efficiency of induced heating of silicon nanoparticles by doping it with germanium, and which has a significantly higher value of imaginary part of the electric constant, which is responsible for light absorption and corresponding heating. So nanoparticles of mixed composition were fabricated by vacuum high temperature annealing of silicon film with a simultaneous deposition of germanium, and as a result of such procedure, silicon germanium, fully alloyed silicon germanium nanoparticles of hemispherical shape were fabricated, and germanium composition, germanium concentration in these nanoparticles is controlled by the duration of its deposition and average size of nanoparticles is dependent on the initial thickness of the silicon film. So, as I mentioned before, imaginary part of the electric constant of silicon germanium differs significantly at green laser wavelengths that is used in Raman setup, and real parts of the electric constant at these wavelengths are pretty much the same. So according to this, two values were calculated. First is proportional to the imaginary part of the electric constant and squared electric field averaged over the non-particle volume, which estimates average efficiency of laser heating of such nanoparticles. And the second value was calculated that is proportional to the force power of the local field in the vicinity of the nanoparticle. This value estimates average SERS enhancement factor of adsorbed molecules. So from these results, we can see that at low germanium concentrations, maximum heating efficiency and SERS enhancement factors are achieved at diameters of nanoparticles around 220 nanometers, where magnetic quadruple resonance is excited. And at higher germanium concentrations, efficiency of laser-induced heating increases due to high ohmic losses. These losses reduce the Q factors of high-order ME modes that leads to a shift of maximum heating efficiency to the diameters of about 200 nanometers, where electric dipole resonance is excited. For silicon germanium alloy, mismatch of silicon and germanium lattice leads to the shift of silicon-silicon band from the initial frequency of monocrystalline silicon. And we can estimate the germanium concentrations from the position of this band. And also this band is temperature dependent. So systematic measurements of this shift value of silicon-silicon band was carried out. So for wide range of densities and for different nanoparticles, different diameters, different germanium concentrations. And the tilt angle of these lines present efficiency of laser-induced heating of nanoparticles. And as we can see, most efficient heating is achieved at diameters of around 200 nanometers at germanium concentrations of about 20%. And finally, experiment was performed to study the influence of nanoparticles heating on the result of SERS measurement. We here also used PATP molecules. Thermogravimetric analysis was performed that measured the temperature, critical temperature of the composition of PATP molecules, which is 130 Kelvin. Then PATP molecules were deposited on silicon germanium nanoparticles, and Raman spectra were measured at two different intensities. And the position of silicon-silicon band helped to measure the average heating temperature of nanoparticles during measurement. So first, little density leads to heating up of nanostructures to the temperature of 420 Kelvin, which is a safe temperature for PATP molecules. And high intensity leads to heating up to 520 Kelvin, which is well above the critical temperature of decomposition of PATP molecules. So from these results, we can see that even a little increase in laser intensity not necessarily leads to the increase of a useful signal of adsorbed molecules, but can, in case of performed experiment, can reduce the intensity of PATP lines. And also, it is important to note that there are no DMAB lines in this spectra, so which tells about chemical inertness of this used substrate. So, a third scientific statement: concentration of germanium in fully alloyed silicon germanium nanoparticles allows to regulate the resonant optical properties and heating efficiency. Optical spectroscopy of thermosensitive non-Raman modes of silicon germanium nanoparticles allows to maintain temperature within analyzed nanostructure system below the threshold of molecule thermal decomposition, providing enhanced and stable SERS yield in the process of measurements. So these main results and main publications on this topic and conferences. These are my conferences. So thank you for your attention.
Good, thank you, Evgeny. So now the talk is open for questions. Please raise your hands, colleagues in the chat, or maybe some colleagues in the audience. So in the meantime, I will start with the first question. So Evgeny, you showed us that the temperature can be measured. The temperature of the nanostructure can be measured by the shift of the Raman peak. And then you showed us that the temperature is distributed homogeneously. And this shift of the Raman peak, as I understood, measures the temperature of the base of the pillar, but not its top. So could you comment why this is the case? Why don't we see the temperature of the peak of the pillar in this Raman spectrum?
We actually measure both and the temperature of the base and the top, but it is the signal is significantly lower. So we just here we can we just add this little band that just makes this peak symmetrical. But so it does not mean that we're not measuring the temperature of the top of the structure. It just adds up a little bit to the overall band.
Yeah, but it's a bit counterintuitive, I would say, because normally I would expect the top radiates most, but the bottom is somehow hidden by the rest of the nanostructure, and it radiates less. But now, in this spectrum which you are showing, we see that the bottom is contributing more signal. So why this is so? Because
it just so it's average temperature of heating temperature just reaches this value. So and it just contributing the most amount to the overall peak.
So roughly speaking, we have more material at the bottom, and that's why we have more contribution to the Raman signal. So
yes, it's basically
good.
Yes.
Thanks.
Maybe here with the same question, this following the previous one. So what is the focusing length? So which part of structure is in the focus?
It is
of the waste.
It is evenly. So just so laser focal spot in that direction is about 1 micrometer. So it's covering all the structure.
Mm-hmm. Partially, probably answers Maxim your question, which is like dependent. There are more material, but it also depends on the focus.
Mm-hmm.
But you didn't try to kind of play with the focus with the focal spot, like refocusing, making like kind of a Z-scan.
Yeah, we could. So I see your point. So we could.
And then your the shape of your peak should change.
If we just make it like from the middle and to the top direction, we should see more contribution of the top of the structure to the peak here.
Yeah, but you didn't.
We didn't play with it.
Okay. Right.
So I've got some other questions. because I have some. But...
Yeah, me either.
Okay, so could you comment, please, Evgeny, why do you choose this molecule like PATP? So is it some conventional choice, or
yes.
There are some special reasons behind that?
Yeah, so I mentioned that it just has it's the most convenient molecule to make this to determine the chemical activity of the substrate. So it's simple, and it is available, and it is widely used for these purposes.
Mm-hmm.
Can you turn on the slide number 9? Yeah. Right. So, and maybe the next one. So it could be the next. No. It shows still slide number 9. So here is what is the field enhancement? Did you have any estimations of the field enhancement at the tip, or Raman enhancement factor?
For the individual
Yes, or maybe average, some kind of estimations. Basically.
Yes, so it is not here in this presentation. So in the work I mentioned this and it's about, if I'm not mistaken, 10 or 20 so enhancement factor is about 10 or 20 times, yeah, for in comparison with the just silicon wafer.
Is it SERS enhancement, or is it field enhancement?
SERS enhancement. So second power of well, not so it's second power. So if we measure in the SERS enhancements, we can so it's about 400. Yeah. So
Okay.
400. Yeah.
Yeah, but it seems so. Can I understand? Do I understand correctly that basically without silver cover you don't see the lines? So you don't see all the lines, or how? Because like on the right, if we compare the 3 figures here, or we just have it we have faster result, or how?
So this, so I mentioned. So first is this is the main result. So just chemically inert substrate, and to be able to measure the chemical reactions in liquids. So we add silver colloid nanoparticles. Right. Yeah, and we see this slow dimerization reaction. This is just a reference, just to know for sure that without nanoparticles we will not see anything. So just PATP molecules. Right. And this metallized surface leads to, so because of high affinity of PATP molecules to the noble metals, so silver in particular, we see that dimerization reactions occurs in the near surface layer of the substrate, but it does not cover all the liquid in the cell. So it just not it is so we cannot for sure see how to tell. So we are not able to track the reactions in the volume of the cell. So we see reaction on the surface, but not in the volume of the cell.
Why can't we say that just the field enhancement and SERS enhancement factor with a thin silver film is just much higher than without film? Isn't that the only kind of a conclusion? And I think theoretically you will have much higher field enhancement factor.
I just didn't get the question.
So basically, how do I see this slide? You take a cuvette with the silver particles, and you see this reaction going on quite slow, like in 4 days. Yeah. Then you remove silver particles, nothing happens. and then you add silver layer, and then you see much faster and more intense chemical reactions. But if you look at the field enhancement factor for silver particles and all those conical conical silicon structures covered with gold, then there will be much higher field enhancement factors and SERS enhancement. So is it that sensitivity of the structure just increased, or chemical reactions went faster?
Both, pretty much.
So but can you distinguish somehow, like, or like, what we see is just the much faster growth of the signal? So
it's I think the most contribution is from chemical SERS enhancement. Yeah. So and but not from the shape of nanostructures or from another factors.
Yeah, but how to independently find that? So
I think it's a little bit tricky,
because you said that that's because of the affinity, because that chemical reactions now occurs in the affinity of gold particle, but it's the same place where your SERS enhancement happens.
So yeah, it's a tricky one. So I can't really answer. So okay. I can tell for sure that it's chemical reactions just because of a gold layer or a silver layer.
Formally, in your statement, you don't discuss the origin of this effect. So it's all right in the sense of formal side of what you defend. Yeah, but the question is, of course, it's probably two factors, but still.
But then I wonder if you change the concentration of the analyte, this obviously affects the rate of chemical reactions because we have Arrhenius law. So in this way, you do the experiment with another concentration of the analyte, you grab this data, and then by comparing two sets of data, you might, it's just a guess, you might discriminate these two ways, two reasons for changing the Raman signal. So this is potentially possible.
I would suggest that you may take another chemical which will not react on the surface, and then make. So it is possible for this chemical to calculate this SERS effect independently.
Yeah, it is. There are many ways to understand this reaction. Yeah, so we can use another analytes. Yeah. Another concentrations.
Okay, I'm done with this slide. Maximum, do you?
Yeah, I'm also done. So
I think I have just probably a few short questions. First of all, the work is very, very nice. I mean, it's very, I would say, comprehensive and thorough.
Of course, you're called for one of the papers.
Yeah, sure. That's the only reason for that. I mean, just probably an educational question. So you've mentioned that SERS improves the intensity by the fourth power of electric field. So I just wonder, if I apply this whatever plasmonic structure and I just double my intensity of laser, I had like 2 milliwatts, then I get 4 milliwatts. What will happen with the intensity of the signal? Will it be doubled or 16 times?
I just need to. So if we double the intensity of incident laser.
Yeah, just an incident laser, not the mode. So this is the.
So I guess it's just second power of this value, of increased value.
So yeah, I think this is So just I think I had some similar question. This is the tricky part of SERS effects. So if you just double the intensity of laser pump, you don't get the enhancement of dramatic enhancement. But if you increase I would say the quality factor of the mode, you will get this power 4 increasement. Okay, and probably I would also agree with Misha and Max when they were asking regarding this broad and pretty narrow response in Raman. I just wonder, have you tried to firstly somehow melt your structure and then try to compare the intensities of initial signal and probably the shape of Raman signal, and afterwards. So after this this melting, when I mean it was in the second part or third part.
Yeah. So.
Yeah. So you've applied for something like 100 plus milliwatts per micrometer, and then I just wonder if you just decrease the intensity, will the shape of your this double peak system, or will it be broader or narrower? Maybe what happens with intensity? So just
This melting occurs quite fast. We really measure the temperature after melting every time, basically. Yeah. So I don't know what we can change to measure something differently.
No, I mean just you increase the. I mean I think you were doing like experiments starting from the very low intensities and increasing.
Yeah.
And then if I go from the maximum intensity back through the same points, I just wonder what will I get.
Yeah, so it's an interesting question. I'm not sure if it will go through the same points. Don't know for sure. Yeah, so we didn't make this curve to see the how it will compare to the if we like make several measurements. Yes, interesting question. Don't know for sure what will happen after this.
Yeah, and probably final, bit general, maybe even a little bit private question. So I just wonder, what are your further plans? Since I've noticed that the papers were mostly published in 18th and 19th year.
Yeah.
So maybe you switch to another topic or.
No, basically. So Raman measurements, SERS measurements, not with PATP molecules, but with different. So we now are working with laser-induced periodic structures, and so they are also semiconductor or metal from metal materials. Yeah, so really rich field for another series of great works.
Yeah, great. I mean. If Sasha Kuchmijak is in the room, then I'm very sorry, but we can suggest, I mean, joining our team of physics department.
You can.
Yeah, sure. That's so fast. Easy, no pressure. But still, before like coming back to your first question, to make it clear, yeah, what Gosha asked, will the Raman intensity be like increased in 4 times when I increase pump intensity in 2 times? No, it will increase in 2 times.
Yes, thank you, Misha.
But you feel it will somehow increase the field enhancement factor in 2 times. Then your SERS signal will be enhanced in 4 times.
Yes.
So it's linear with the coordinates. So it's a good question to like to make it clear. Yeah? You will not. It's linear with the regarding the pumping intensity, but square, but parabolic with regard to field enhancement factor, which is internal geometrical, let's say here, property of.
So Eugene just perfectly answered.
Yeah. So
this,
just
this okay.
to speak that out. Maxim, have you got a question? I still have some.
Please.
Ryan, can you turn on 17th slide number 17? Yeah, here and also in generally. So how did you rely? How did you claim that? So you claim that this is a solid mixture, right?
Yeah.
What kind of measurements did you make to?
So there were X-ray spectroscopy measurements, and we saw that it was, and also the FIB cuts to see that there are no like areas of different compositions. So it's even. So it's just clear one cut and even distribution of material. Yes.
So but how precisely you can control the ratio, the stoichiometric ratio in the?
of germanium to silicon, about half of percent, around this.
So you basically have different technological process, and then you can get.
We just have different deposition
concentration or thickness.
So we deposit it in a deep for 10 seconds, for 20 seconds. So we just by the deposition time, yeah. So we can change this concentration.
And X can vary from which from what. So are these the achievable numbers from 0 to 0.3?
So achievable, yeah. So we can make it more, but so it higher, more than 0.3 germanium concentration. Raman bands of so they become flatter, and it's difficult to measure the position of peak and precisely, and also the field distribution is not that good. So just optical properties of these particles just become so basically enhancement factor of in these nanoparticles is lowers with the germanium concentration.
I also have questions regarding the right side figures. So first of all, E out, is it what is it, the maximal field, or what is it?
It's just averaged field in this in the vicinity of the nanoparticle.
Is the average too, right?
Like around 5 or 10 nanometers.
And it's not. So there is no gold, right? So it's just
silicon germanium.
Okay. So, but you still have got quite a strong field enhancement there.
Yeah.
Yes.
Not like very big, but just enough to have great enhancement factors.
And then the bottom figure. So, what is it averaged field inside the structure, or what is it? So there is inside
the volume of the overall volume of the nanostructure.
Okay. Yeah. And then the inside figure just shows the field distribution, or how?
Yeah, yes. For the diameter of about 200 nanometers.
Okay. Yeah. All right. Yeah.
Sorry, may I ask please about this down right picture? Here you estimate the efficiency of laser heating by estimating the absorbed power in the structure. Yes, and if I understand right, there should be also some maybe estimations about radiative and non-radiative losses in the because if we consider this like an optical resonator, then the efficiency should be cover two factors, I guess, in semiconductor structures.
Yes. So just consult calculations, and we did not make so we didn't cover this question. Yes. So we just make the calculation that tells us about the efficiency. We don't look into the nature of this heat efficiency. Yeah.
But this is the temperature increase, or it's the absorbed power?
Absorbed power. Yeah. So it's just estimation of absorbed power. Yeah. It's not like real values, but just enough to estimate.
Good. Thank you, Evgeny. So I do not see other questions. I suggest we conclude now So we take some break in the seminars due to long New Year holidays, break for 2 weeks. And then on the 12th of January, we go on with the talk of Andrea Armaroli, invited by Andrei Bogdanov. So stay with us and have nice New Year holidays, Christmas, and all the celebrations. Thank you to everyone.
Yeah, thank you, Zhenya. Thank you, Maxim.
Yeah, so we'll see you next time.